circular and spherical motion. So you're in circular or spherical motion anytime an object remains a fixed distance from some reference point. That fixed distance would be the radius of the sphere, the circle. The difference between circular and spherical is if the object stays in a plane, if the object is confined to a plane, then the motion is confined to a circle around that reference point. So this is circular motion. And if the motion isn't confined to a plane, so it moves in 3D, then that's spherical motion. But if you think about an infinitesimal time interval, time interval, dt, the object remains in a plane for either one of those two motions. So the object is confined to a plane in other words, it's staying along a circular path, not a spherical path. For circular or spherical motion. And so what you have, if this is the circular path, okay, we're talking about some infinitesimal time interval. So how far does an object move over an infinitesimal time interval? Far or not far? Not far, correct. So you get, and that looks, let me make it look smaller, but so the object over that time interval dt tracks out some arc of the circle like this, and we're going to define that by this infinitesimal change in angle d theta. Okay, so the object's moving this way along the circle. If you were thinking about a longer time interval than this infinitesimal dt, then the thing would veer off of that circle if it was spherical. If it was circular, it would stay on that circular path. But for spherical motion, it would veer off and be on a new plane or whatever. It's going all over the place. But just for that little tiny fragment of time, it stays in a circular path. Okay, so we can use this idea to define the angular velocity, which is going to be a big deal for this, for circular and spherical motion. So then the angular velocity omega lowercase omega. And notice this is a vector. Okay, so vectors have two properties, magnitude and direction. Okay, so we're going to think about the magnitude and the direction of this. It has a magnitude that's equal to the absolute value of d theta dt. Okay, obviously that's a derivative, but if you just think about this, like if you're trying to make sense out of it intuitively, just think about that tiny sliver of a motion d theta, that tiny change in angle, and divided by that tiny change in time dt, and that's the magnitude. And the direction follows the right-hand rule. Okay, so if this thing, if you imagine, you got that written down. Let me go back to this circle. So even though this is just a tiny infinitesimal even sliver of this circular path, to figure out the direction, just imagine the full circular path and make your fingers curl in the direction of that circular path, and your thumb gives the direction of the angular velocity. So the direction of the angular velocity vector is always normal to the circular path at that instant. Okay. So if your fingers do this, the direction is out of the board. Any questions about that? Yeah.
So just to understand that concept, basically we're just doing a vector for circular motion, correct?
Yeah, it's the angular velocity. So it's telling you how fast the angular position is changing, how fast, and it doesn't matter how big that circle is, it's just talking about the angle, you know? So even if the circle is tiny, obviously the speed would be a lot smaller because, say, over 1 second, it goes over through the circumference of the circle, but that circumference is tiny.
Right.
Whereas if you expand way out, something would be going really fast that's going over a big circle, but if the angle is changing the same amount over the same time, then the angular velocity is the same. Yeah. Okay, and what does this say about the units? Well, it's a change in angle over a change in time. So this is going to be radians over time. And that means that if you're doing it in SI units, it's radians per second. And remember that radians are sort of a funny unit. It's really just a purely mathematical description of an angle. So I use radians to remind you that we are talking about an angle, but that's really the same thing as just 1 over second. Okay. Okay, so let's think about how this works. So let's say we have an object moving in a circular path like this. And let's say that's in a coordinate system where the y-axis points that way, the x-axis points that way, and z is sort of out towards us. And let's say that the particle is moving at 1 revolution per second. What's the angular velocity vector? Well, 1 revolution is 2 pi radians. So we have 1 revolution per second, where 1 revolution is 2 pi radians. And so that's 2 pi radians per second. And that's the magnitude of the angular velocity vector. So I can write that. Magnitude of a vector is use the absolute value symbol. And now we have to figure out the direction. So use the right-hand rule with that circular path. So what's the direction of the angular velocity vector? Up. Yep, exactly. So the direction, since it's going this way, the right-hand rule says that's the way your thumb goes. And so the angular velocity is 0, 2 pi, 0. And you can think of that as we multiplied the magnitude times a unit vector in the direction that we found from the right-hand rule. So there's the magnitude. There's the direction. Let's define angular acceleration. Okay, angular acceleration, and the symbol for that is the Greek letter lowercase alpha, and that's also a vector. And in general, it'll be a function of time. And that is defined as the time derivative of the angular velocity vector. Okay, so now if you're in circular motion, the angular velocity and the angular acceleration are parallel. So each of those is perpendicular to the circular path. These are vectors. If they're the same direction, so for two vectors that are parallel, there's two possibilities. They can either be in the same direction or they can be in opposite directions. Okay. If they're in the same direction, that means that the rotations are speeding up. And if they're in opposite directions, the rotations are slowing down. If you're not in circular motion, you're in general spherical motion. Then there's no restriction on the directions of those two. They don't have to be parallel. So omega and alpha don't have to be parallel. Now that we have all that, let me give the units. So the units for angular acceleration are radians over time squared. And that means that the SI units are radians per second squared, or you can think of it as just 1 over second squared. All right, so now that we have these two new rotational quantities defined, here are the two important equations that are going to come up in every circular or spherical motion problem. So for any object in circular or spherical motion, the velocity of the object is the angular velocity crossed with this vector r, and I'll talk about what this vector r is in a second. And the acceleration of that object, of that particle, is the angular acceleration crossed with the r vector plus omega, the angular velocity, crossed with the quantity omega cross r. Okay, so these are kind of the two equations that define circular and spherical motion. This r vector is the instantaneous vector from the center of the motion to the particle. So I say instantaneous because as this thing moves around in its circular path, that's a vector that goes from the center of the circle or the sphere to the object. And so at every instant, that r vector is changing. you know, as the object moves around this circular, you know, perimeter or the spherical shell, you can imagine it. Have you ever seen these equations before? Probably you didn't see it exactly in that form, or maybe you did kind of in passing. But these are, you've dealt with circular motion before in physics 1. So notice that what you saw in physics 1 was that the magnitude of the velocity, the speed of an object, was equal to the radius of the circular path times the magnitude of the angular velocity. Okay, and then the direction you had to do for yourself. If you're dealing with it in the XY plane, then it's just going to be in the positive Z or negative Z direction. Okay. Well, now these equations, it's the same formula, but doing it with the vectors and the cross product, it gives you the direction. You don't have to think about the right-hand rule and stuff. It'll do it for you. Okay. The acceleration vector, the way you did that in physics 1 was you said that there's some centripetal acceleration. Okay. The centripetal acceleration is the angular velocity squared times the radius of the circle. Well, this is the centripetal acceleration now, and the direction is done for you. Okay, you don't have to think about the direction. And then there was also a part of the acceleration that was tangential that determined whether the object was speeding up or slowing down. And that was the angular acceleration times the radius of the circle. And then you use the right-hand rule to figure out the direction. Well, the direction's done for you here. Okay. So this is the tangential acceleration. And this is the centripetal acceleration. Yeah, you add them. So the way it worked in physics 1 was, so if you had a particle moving along a circular path, and here's the center, and let's say the instant that you're thinking about the object is here, and let's say the velocity is this way. And let's say that it's slowing down, then the tangential acceleration is this way. The centripetal acceleration is always toward the center. And so you come up with the components of the tangential acceleration, come up with the components of the centripetal acceleration, and then you add those components together to get the total acceleration. Okay, well, let's do an example. So let's say a child is on like a playground carousel. Well, they don't make those anymore, I don't think, because it injures 85% of the kids who look at it, but they used to have these things. So there's a child on a carousel with a radius of 2 meters. Actually, my kid was at baseball practice a couple of years ago, and we went to we had baseball practice at this park that had a carousel, and all the kids are like, "Oh my God, what is that?" And the coaches are like, "Oh, we used to have those when we were kids, and like, get on," and I'll spin it, and like one of the kids flew off, and like hit his head on a rock or something. Like, that's just what they do. Okay, so at a given instant, the carousel is rotating counterclockwise, looking at it from above. With an angular speed, so that's the magnitude of the angular velocity, of 2.5 radians per second, and slowing down with an angular acceleration magnitude of 9.5 radians per second squared. And we want to calculate the velocity and the acceleration at that instant. And in physics 1, you did problems like this, but we're going to use those vector equations now, okay? All right, so here's the circular path. And it doesn't give a single location on the circular path. I'm gonna use this here. So this is the kid, but that was an arbitrary choice. And the coordinate system I'm going to use is this. At this instant, it's rotating counterclockwise, so the angular velocity is counterclockwise. And it's slowing down, which means that the angular acceleration has to be clockwise. They have to be opposite. Those are not vectors, actually. I mean, omega and alpha are vectors, but we're gonna have to come up with the components. But those are just sort of describing them as a circular path. The vector is just an arrow, either out of the board or into the board. Okay. Okay, so first, let's do the velocity. So the velocity is the angular velocity crossed with r. This is the kid down here. This is the center of the circular motion. So for that omega vector, we're given the magnitude is 2.5 radians per second. All we have to do is come up with the direction. Okay. So if it's rotating in this direction, okay, curl your fingers in the direction of rotation, and that means that your thumb is coming out of the board, which has to be the positive z direction. So the angular velocity is 2.5 radians per second times the unit vector in the direction, which is 0, 0, 1. And so the angular velocity is 0, 0, 2.5 in radians per second. R vector. So what's the vector that goes from the center of the circle to the kid? So it's in the negative y direction. The radius is 2. So it's going to be 0, negative 2, 0. Yeah, of the radius of the carousel. Okay, so this is 0, negative 2, 0, and this is in meters. So the velocity is 0, 0, 2.5 crossed with 0, negative 2, 0. And that is 5.000 in meters per second. Yeah, it's cool. Yeah, it's a very powerful thing. Wait till you see the next step. It's gonna. Okay. So does it make sense that the kid's velocity at this instant is in the positive x direction? Yeah, that's where it has to be. Tangent to the circle in the direction that it's rotating. Yes. I will not mark you off for that, but I would recommend using this notation because it's in a form that then you can use rotation matrices and other things. But no, I won't mark you off for the form you use. Any other questions? Yeah.
You're saying the unit radians like squared?
That's for angular acceleration.
Exactly. All right. So is there a formula for spherical?
It's the same. It's the exact same formula. It just comes out in different directions. Yep. Any other questions? Okay, so now let's calculate the acceleration. Well, we have the angular velocity already. We need to come up with the angular acceleration. So we're told that the magnitude of the angular acceleration is 9.5 radians per second squared. We already figured out that since it's slowing down, that means that it's that the angular acceleration is this way. So use the right-hand rule, okay? And that means it's going into the page. Yeah, so negative, so you can think of the angular acceleration vector as 9.5 times 0, 0, negative 1. And so you get 0, 0, negative 9.5. And this is radians per second squared. And we already have the angular velocity and the r vector from part A. So the acceleration of that point is alpha cross r. So 0, 0, negative 9.5 crossed with the r vector, 0, negative 2, 0. And then plus the angular velocity vector, 0, 0, 2.5, crossed with the quantity, 0, 0, 2.5, cross 0, negative 2, 0. This is actually what we did before. So we get, if you cross those, you get 5, 0, 0. And then if you cross 0, 0, 2.5 with 5, 0, 0, you get 0, positive 7.5, 0, I think. Oh no, 12.5. And then if you take the cross product of these two, you get negative 19, 0, 0. And now we're just adding these two together, and we get an acceleration vector of negative 19, positive 12.5, 0, and the units are meter per second squared. And so if you knew the kid's mass, you could figure out what net force is acting on the kid. If you had a way to break up all the forces, you could figure out what kind of friction would be required not to slide off, that kind of thing. Okay. Calculating the acceleration is going to be really important because acceleration is how you get from kinematics to kinetics, okay, through Newton's second law. So this equation is going to come up all the time. So this acceleration equal to alpha cross r plus omega cross quantity omega cross r. I call this the watermelon equation because it helps me remember the order of things. So if you think of alpha as A and omega as W, I always think of this as all ripe watermelons will rot. Sort of a pessimistic view of things, but a couple of things just to make connections with this example problem. Is this circular motion or spherical motion? Circular. And so what should that say about the directions of omega and alpha? They need to be parallel. And in this case, it's slowing down. So should they be in the same direction or the opposite direction? Opposite. And so look at, we have 0, 0, 2.5 for omega. That's in the positive z direction. Alpha, 0, 0, negative 9.5. So that's in the negative z direction. So they're opposite.